I'll put out some old exams for you so you have something to look at. Then you can see what I expect from you on the exam. Today the topic is turbulence. You have been given some material, turbulence 1 and 2, and also some lecture notes, turbulence modeling, and should be one more. Why isn't he here? Strange. I'll put it up later. One more about DNS. So today we start with some slides. So the cute one I found in a book about chaos. So you have more and more unknowns to the right, and more non-linear problems, more and more difficult down. So you start up in the left corner, very easy problems, and then it becomes more and more complex. So chaos, strange attractors, model growth, you can find here. So that sort of was the focus on this book. Frontier, meaning now we are talking research inside this area here. So for continuum problems, most difficult, we have viscous fluids down here, and then waves, and then all down here we talk about turbulence, and then life. I think this is wrong, this should be switched. Absolutely. I mean, Einstein looked into turbulence and he gave up. He said it was too difficult. Turbulence is tricky. So that's just the introduction. So what is turbulence? Well, actually we don't have any clear definition of turbulence. So it's more like porn. What is porn? What is art? Well, you can't really tell, but you know it when you see it. Sort of the same with turbulence. We define turbulence as a flow with all of these characteristics. The flow is always diffusive, high degree of mixing. It's a large Reynolds number phenomenon. We have a lot of vorticity and a lot of different scales in all the different vortices. It is a three-dimensional concept. So if you're talking a 2D simulation, it's not turbulent, unless of course you use a model to cheat it. But the turbulence in nature is always three-dimensional. It's always dissipative, stealing energy. It costs more to push a turbulent flow through a pipe than laminar, much more. It's a continuum phenomenon. And finally, transient. So steady state, no, that's not turbulent. It's always transient. So I know the students, they always get confused when we talk about vortices, say flow around a cylinder. Well, you get this nice von Karman vortex streak behind it. That's not turbulence. That's laminar vortices. They are structured and nice, fair enough. They have vorticity. They are transient, but they are only two-dimensional, and the Reynolds number is not that big. So no, it's not turbulent. They are laminar structures, unsteady laminar structures. So turbulence, all of these has to be present. Okay, now we don't need him for a while. thing about turbulence. We believe that the Navier-Stokes equations describes turbulence. You can't really prove it, but nobody else has said or found anything else. So no disproof exists, hence we believe it. The Navier-Stokes will cover the turbulent motion. So we just need to solve the Navier-Stokes. So how do we do that? Just an overview, turbulence models. So here I will just make a brief list, starting with a very easy model and then more and more complex models as we go down. So the first one, what should we call it? Correlations. You have a turbulence model saying that you take your kinematic viscosity and you multiply it with 1,000 or 10,000 or 100,000. That's actually a turbulence model. Of course, you are simulating a totally different fluid than original, but you can have now a Reynolds number based on the real viscosity. It can be a big Reynolds number. But then you increase the viscosity in the problem so much that actually it switches over and becomes laminar, and you can solve it easily with a laminar code. You don't need anything else. So, very bad model indeed. We have some integral models. You have this from Kahneman integrated momentum equation for flow along the inside a plate. And here also I would say Bernoulli with losses. These loss terms, and they should account for the turbulence. Engineering tools, okay, but they work plus minus 15–20%. So widely used, yes. And then we are talking zero equation models. Well, actually, before we do that, we should call it Reynolds averaged Navier-Stokes. Reynolds for short. So that's a very big family, and there normally you will find your turbulence models. And then as a subfamily, zero equation model, meaning you don't have a transport equation of any turbulent quantity. You don't move a turbulent quantity from one place to another. So this means if you create turbulence somewhere, you have to destroy it in the same spot. It doesn't move around. Here you have a lot of models, Prandtl's mixing length, Sebesi and Smith, you have a whole bunch of these, which will typically create a turbulent eddy viscosity for you, equal to, and then something already unknown in your problem, like a velocity gradient or something. So nu t, sort of an eddy viscosity. So you could think in terms here of also the same, this eddy viscosity. It's not a real viscosity, but it sort of appears like it. So here we have a model describing him, but as I say, no transport of any turbulent quantity. One equations model, there you're talking transport equation. And the one famous one will be the K transport of turbulent kinetic energy K. And a transport equation you can always write in the form production, and you have diffusion, and then minus dissipation. Something that produces the quantity, something that diffuses it, spread it around, and something that destroys it. And it's also possible here to have more terms. K here being the turbulent kinetic energy. So yes, this is one equation that has been used to some extent. You have another one, Spallad Almaraz, where they have a transport equation for this eddy viscosity. And then the same terms on the other side. That one is quite famous. Good for airfoils, very easy to handle, easy with the boundary conditions, not a problem at all. And then finally, two equation model. And here you will find the most famous K epsilon. You have two separate quantities that we play around with. You need two additional transport equations. Remember the Navier-Stokes, that will be three transport equations, one in each direction, plus the continuity. So here you have two additional equations, one for K, turbulent kinetic energy, and here the turbulent dissipation, epsilon that destroys the K. You have others here as well, K omega, omega being a turbulent frequency. And more famous and the new one, K omega SST, where you combine those two. You try to use the different method where he is good. K omega, very good close to the walls. K epsilon, very good in the free stream, outside the boundary layers. So the combination of these two, K omega SST, is quite famous nowadays. And you have other options as well. K eddy viscosity, you have many of these. But definitely the most famous, most widely used, K epsilon. And the reason then why he is so famous and popular is not that it's a good model. Actually it's terrible, but it was sort of the first model, a little bit advanced model, that had any degree of success. So people used it a lot and always refer to it. So you'll find a lot of validation and verification on it. So if you have a case, you can always find a similar case where somebody has used K epsilon. So you have a lot of reference data for it. So I mean, of course, that's also important here choosing the correct turbulence model. And here I would say the industry stops. If you're using K epsilon, they will say, wow, this is really advanced, this must be the gospel truth. Oh, very good. The researchers, we don't look at this side at all. And the ASM, yeah, okay, we can do some research with ASM. That's an algebraic stress model. And here a full RSM. I'll come back to what these actually represents. To say it quickly, the RSM, there you have transport equations for all your 6 Reynolds stresses, and they look something like this: rho, U, fluct, V fluct, averaged, equal to yada yada yada. So this will represent 7 transport equations in addition to the Navier-Stokes. You need one of these, one for each of these 6, plus dissipation equation as well. The ASM, algebraic Reynolds stress model, is sort of an average between the K epsilon and the full RSM. So you solve first using K epsilon, then you use just algebraic equation systems to find the behavior for all these 6 unknown Reynolds stresses. So here, fairly advanced modeling. And then I would stop within this RANS family and jump to the next level where we have LES, large eddy simulation. And finally, the most advanced, DNS, direct numerical simulation. So this is sort of an overview over different turbulence models. They should be more and more advanced and should cover more and more physics, more and more correct. That's not necessarily entirely true. Like Prandtl's mixing length, you typically have one constant you can play around with. Then, of course, depending on the problem, you can switch him to a number which is suitable for your problem. And here's Spalard-Almaraz, for instance. You have a couple of constants inside it. You can tune this model for your problem. In a full RSM, you have 25 parameters you can play around with. So that's not so easy. Then you really have to focus on your problem and see if you can find a set of constants, coefficients, that is suitable for your problem. That can be hard to find. And here, starting with a parameter investigation with 25 parameters, well, you can take a lot of PhDs there. So that's heavy. LAS, not that many parameters, and DNS, no parameters at all. There we solve the Navier-Stokes, all the way down to the turbulent length and time scales. That's the philosophy. Come back to that later. So this just for an overview. Any questions to this one? Then let us have a look at the material. Turbulence 1 and 2, they're sort of connected, and what's important for you will be mainly the first part. That is where you find most of the theory. Part 2, 3 and 4, they are just articles where you can see sort of examples where typically where the classical industrial advanced turbulence models fail, and we have to use more advanced models. The last one here, that is actually something we wrote for a mathematical journal, trying to explain the problems then operating with the DNS. Trouble with the DNS is you have tremendous amount of data thrown in your face, so how to find the answers can be a little tricky. Also, you find the lecture notes on turbulence modeling, something I stole from Helge Andersson, and discusses briefly a little bit more of here the different turbulence models that I've just listed. So you can have a look at this if you are interested. So we will sort of start on the two equation models directly and focusing on these, and then more advanced models. But if you need a little bit more background, then I can recommend this one, fairly straight to the point. So be my guest.
That is in the web page as well?
Sorry?
That one is on this one as well?
It should be. Yeah, lecture notes. Yeah, it's the last one. So, this theory part here, as you see, is written for a conference they had here within turbo machinery, pumps, turbines. So it's from '87, fairly old, but it was sort of a nice overview over what we need here, I think. So I kept this. It's an old typewriter age, but still readable. So we're sort of focusing a little bit on what we need on the two equation models, and then also the Reynolds stress modeling and the algebraic stress models. So this is our focus. Yeah, I won't just go through the introduction here. The equation of motion. So again, it is generally accepted that Navier-Stokes is capable of describing turbulent flow. So we still believe it. We can't really prove it, but we believe it. Now, about the Reynolds averaged mean motion equation. The chapter 3 that I had on the whiteboard, the Reynolds family. So the philosophy sort of listed here, but I can give you a brief overview of it. I guess some of you know it already, but if you've never seen this before, then it is quite essential for the family number 3. How to create the Reynolds equations. Reynolds averaged Navier-Stokes equations. You go in the lab and you bring a pitot tube or something, and then you put it into a flow, and then you measure the velocity. Measure u as a function of time. And the signal you get, well, a pitot tube is rather slow actually, so maybe you should use a more advanced measurement technique. Never mind that, the real velocity can go something like this. It can behave rather fluctuating, and typically we will not be interested here in all this noise. We will be interested in the average velocity. And here, say I want this behavior like this. This is what I am interested in. So the blue one here being a large u. He may be constant or he may change with time. But he should then change slowly. So how to create him? Well, you invent or imagine a time window here, a delta t. And then you say my average velocity will now be 1 over delta t, and then the time integral of u dt from t to t plus delta t. And then the size of this time window can sort of give you the time dependency of the mean function. If you have a very big window, of course you won't see this change at all, then it'll just be one constant here. So a little bit your choice. Actually, in practice, you never put a number on this delta t in seconds, you never use it. unless you are in the lab then, okay, then you can measure it when you have a real signal. In turbulence modeling, we don't have to sort of use this window to anything. We just assume that it's there, meaning you take the real velocity that you have, and then you split it up into the mean part plus the rest, the fluctuating part. And you do the same with all quantities. Pressure, a large pressure plus fluctuating pressure, density, whatever, temperature, everything you split up into a mean part and a fluctuating part. And then now we say the fluctuating part, that's boring, uninteresting for an engineer. I want an answer here. I want the big U, the big pressure, for instance. Having done this split, we'll look at the equations of motion. So I just pick one component here, u dx, v du dy equals, we have the pressure gradient, and then viscosity, double derivative with respect to x, for instance. Now insert your split into a mean and an average part. Yes, you can do that. Of course, this equation now will be twice as long, so still not so interesting. But what we then are going to do is to take a time average. So we sort of define here, time averaged. When you have a quantity, you just put a bar on top of it. That means we time average it. That means if I take the large U and take a time average, nothing changes. It will be the same. I mean, that's sort of the definition for the mean velocity, or the mean pressure for that matter. It doesn't change at all. If you take the fluctuating part and then you take a time average of him, you will, per definition, get zero, of course. Also then, if you take the time average of the real velocity, the real U that we have up here, okay, you are only left with the mean. So that's sort of one way to get rid of all this fluctuating, uninteresting, turbulent noise. So the idea now is to find this equation written for only the mean properties. So that's what we want. So what we do, we insert all our variables with this mean and fluctuating part, and then take a time average of the entire equation. And then, if you have little statistics, taking the average of a sum will now be the same as averaging those two first. Also, if you have a quantity and you want to take the time derivative, space derivative, or time derivative for that matter, it's the same as make an average first and then take the derivative, and so on. So this is sort of simple statistics, simple math. Well, if we now start, what do we get here? Well, you will have time derivative of large U plus U fluct, plus, and so on. Large U fluct multiplied with x derivative of large U fluct. And then a large V plus V fluct multiplied with y derivative of large U plus U fluct equals x derivative of big pressure plus fluctuating pressure and the final term, double derivative of large U plus U float. And then you take a bar over the entire equation, which is the same as to take the bar over the separate terms, which is the same as to take a bar over whatever is inside your equation system. But here we have to be careful. This one, we have to actually do it like this. And also this one. Here, not a problem. Here, not a problem. And of course, all these sums here, they can be split up. So this one is going to be 0, this one is going to be 0, and this one is going to be 0. So there you will get what you are seeking, an equation for the mean properties alone. The problem is these convective terms. They are nonlinear. There something fishy is going to happen. So if you rewrite them, take this term, you will have the large one, large U du dx. You will give a contribution, yes. And then you will have, say, this one multiplied with d large U dx, and then the other one, large U flocked dx, and finally U flocked dx. And then take a time average. Well, first term here will survive. That's the one we want anyway, so that's okay. This one, time average, will disappear because the average of one single fluctuating quantity disappears. Same with him. He will also disappear. But this guy, he survives. There you have a product of two fluctuating quantities. When you multiply them, you don't get 0 anymore. So he will survive. And for this term, you get exactly the same. You will have the big one, V du dx. So they will survive. But wherever you have just one single turbulent or fluctuating quantity, time average, he will disappear. But we are left with V flocked, du flocked, dy. He will also survive. So these two are sort of the unwanted new guests that appeared in the equation. We don't like them because we really have no idea how to handle them. Of course, it should be time averaged. Also, what we do, we rewrite them on the conservative form typically, so they will have ddx and ddy in front of them, and inside u flocked square, and here u flocked v flocked. So what do we end up with? Well, our original equation, after doing this time averaged, will look something like this. You'll have large U, time derivative, and then this one, who now reads ddx of u flocked square, and then this one, dy of u flocked v flocked, time averaged here, and then of course the terms that we wanted, they will also appear here. Ordinary U, large U, du dx, large V, du dy equals, and the other side, well, that's just the average quantities directly. Viscosity and double derivative of large U dx square. So these two terms are what sort of describes the turbulence, actually. Any questions so far? That's okay? So please note these two terms. they are born from these convective acceleration terms, so they are actually accelerations. Nevertheless, we throw them on the other side of the equation system. So that our Rans equation will look something like this. So this one now looks something like this. I just write it for short, du dt. That is this term and these two terms equals, and on the other side, minus 1 over rho the pressure dx, and then we will rewrite this term. Well, actually, we should write it like this to have it more correct. Multiply the equation with density. And then you will have plus d dx of viscosity times du dx. Well, now it should be the other viscosity. Well, we can cheat. And then you will have something minus. And here comes now a tensor u flogged I, u flogged j, time averaged. So now, depending on which equation you are looking at, that should be j and j. Depending on which equation you're looking at, you have to put in the correct Reynolds stress. So the rho ui flogged uj flogged time averaged is what we call a Reynolds stress. And of course it's not a stress like a viscous stress or shear stress or whatever. It's an acceleration. We just throw in on the other side because he is going to join these terms anyway when we talk about turbulence modeling normally. Okay, that was the birth of the Reynolds stresses, and here you have now the Reynolds average Navier-Stokes with some additional term. And a turbulence model, its only focus is find an expression for this one that I can handle. Now this will represent 6 unknown functions, which we have very little hope to find, but we'll try. Any questions to this one? That was okay? So the notation here is widely used. Small letter, the real quantity. Large one, that's the mean. And then a fluctuating, just a little stroke, meaning the fluctuating part, the turbulent part. So our Reynolds average Navier-Stokes listed here. And here written with the viscous stresses as a sigma, and then the Reynolds stresses here. Okay. So the Reynolds stresses, typically denoted with a small tau, ij, is then this tensor. So it's a symmetrical tensor, so it's not 9 functions, it's only 6. Although it's a 3 by 3 matrix, of course. But it's a symmetrical one. So we call them stresses. Sort of, as it says here, they act as an apparent turbulent stress, sort of an apparent diffusion mechanism. We talked about that, all the different diffusion mechanisms that we had. And then turbulence, yes, it can also be treated as a diffusion mechanism. Damping down, smearing out sharp gradients, and so on. And a turbulence model is now to find an expression for these Reynolds stresses that can be used. Okay, any questions so far? Straightforward? Good. For the simpler models, the cheaper models, all the way down to K epsilon, the two equation models, they will be based on this eddy viscosity hypothesis, where we say that we can represent all these Reynolds stresses with an eddy viscosity. This eddy viscosity thing, that's a little abstract. What should you think about? Viscosity that has to do with turbulent vortices with different scales, how they interact. Yeah, maybe, I'm not so sure. But then multiplied with the total strain of the mean velocity field. Now remember, the large U's here, they are unknown already. So doing this, you go from 6 unknown functions to 1. That's fairly decent. Now we have only 1 unknown function instead of 6. So quite crudely, of course, but very efficient. Although we have a small k here on the other side. Well, actually, he should also be an unknown, shouldn't he? The k being the turbulent kinetic energy. And here it is written wrong. This is not correct. K is 1/2 of ui fluct multiplied with ui. Must be the same index. Then you sum over all possible combinations, so it will be u fluct square plus v fluct square plus w fluct square, and then 1/2. So it's kinetic energy, but just for the fluctuating velocity. So of course 1/2 and then the velocity squared. But then you should sum all 3 components squared. So ui should be, that's all. So yes, he will now, at least for now, represent 1 unknown. And then this eddy viscosity function, whatever that is also an unknown. So we have 2 unknown functions, if we want to use this hypothesis. And it's not so stupid, actually. In philosophy, a little bit like this turbulent behavior, he acts like a stress, acts like a diffusion mechanism. So he sort of belong together with the molecular viscosity. If you think of the basic equation that we had somewhere here. How does he look? Well, written on this form, it should be rho times the kinematic viscosity, and then you will get the exact same, this stress that we had already. This parenthesis, the big parenthesis here. So it's sort of the exact same recipe. It's only the molecular viscosity then that is here. So it's very easy then to join these two together. You just say it's viscosity plus the turbulent viscosity. That's all. That's the only trick you have to do in Navier-Stokes to get the model in. Except this one, of course. The Kronecker here, sort of just a switch. So when I equals j, he will be 1. When they are different, he will be 0. Okay, we are down to 2 additional unknowns that we have to model, quantify. Okay, we take a break here.